Welcome back to today's Explainer. We're jumping right into 12 Chemistry, Unit 6, focusing specifically on Section 6.7. That's the classification of point defects. This is a massive, high-yield topic, and it was actually asked in the June 26 PY paper. So if you want to lock in those marks, let's get into it. Here is our quick roadmap for today. First, our intro to 12 Chemistry, Unit 6. Then we'll look at point defect classification, compare Schottky and Frankel defects, tackle some past year theory questions, run through the 1-mark PYQ challenge, and finish up with the TOT guide practice.
Section 1. Intro to 12 Chemistry Unit 6.
Section 2. Point defect classification. All right, looking right at this PDF on screen, we're going to read this line by line. The classification of point defects branches cleanly into 3 main types. Moving left to right, we've got A, stoichiometric or intrinsic or thermodynamic defects. Then B, non-stoichiometric defects. And finally, C, impurity defects. You'll also notice that stoichiometric branches down further into Schottky and Frankel defects, while non-stoichiometric splits into metal excess and metal deficiency defects.
Now, what is the big secret tying all 3 of these branches, A, B, and C, together? Well, it's explicitly stated for every single category. They must maintain electrical neutrality, so the number of positive ions absolutely has to equal the number of negative ions. No matter how messed up the crystal structure gets, the overall charge stays perfectly balanced. It's a foundational rule.
Section 3. Schottky versus Frankel defects. Let's break down the core mechanisms here. On the left, the text explains that the Schottky defect arises due to the missing of an equal number of cations, the positives, and anions, the negatives, from the crystal lattice. They are literally just gone. But on the right, the Frankel defect arises due to the dislocation of ions from its crystal lattice, occupying an interstitial position. Basically, the ion hasn't left the building, it's just squeezed into a tight, abnormal spot.
And here's how that actually plays out in the real world. With Schottky defects, because those ions are missing entirely, it lowers the density. You'll see this when the positive ion size is roughly equal to the negative ion size, like an NaCl. But with Frankel defects, because the ion just moved to a different spot inside, it does not affect the density at all. This usually happens when the positive ion size is much smaller, like an AgBr. You can literally see this happening in these atomic diagrams from the source. Look at the Schottky side on the left. You see those empty circles? The diagram explicitly points out one Cl- missing and one Na+ missing, total physical gaps in the grid. Now look at the Frankel side on the right. The edges are totally fine, but right there in the middle, it points to an Ag+ in an interstitial position. It's just shoved in there. Super easy to visualize.
Section 4. Past year theory questions. All right, let's look at question number 9. It simply asks, explain Schottky defect. Super straightforward, right? But it's heavily tested. The source notes this came up in the September 2020 and March 23 PY papers. For this one, you just need to hit the key points we covered: missing equal cations and anions, lower density, and use NaCl as your primary example. Then we have question number 24. Write a note on Frankel defect. This one is insanely popular. The document lists it for August 2022, March 23, June 25, and as we said earlier, the June 26 PY paper. Examiners just love testing you on that dislocation and density stability concept, for sure. Section 5. The 1-mark PYQ challenge. Let's read line by line for question number 19. Schottky defect in a crystal is observed when? Is it A, unequal number of anions and cations are missing? B, equal number of cations and anions are missing from the lattice? C, an ion leaves its normal site and occupies an interstitial site? Or D, no ion is missing from its lattice? Take a second and lock it in.
And the correct answer is B. Equal number of cations and anions are missing from the lattice. If you remembered our comparison table, you absolutely nailed it. That's exactly what keeps the electrical neutrality balanced.
Moving right along to question number 20. The cation leaves its normal position in the crystal and moves to some interstitial position. The defect in the crystal is known as. Let's look at the options. A, Schottky defect. B, F-center. C, Frankel defect. Or D, non-stoichiometric defect. What's your guess? The correct answer here is C, the Frankel defect. The dead giveaway is that phrase, interstitial position. The ion just dislocates. It doesn't actually leave the crystal at all. Okay, let's try a trickier format with question number 21, which is a March 26 PY question. The assertion is, due to Frankel defect, density of the crystalline solid decreases. The reason given is, in Frankel defect, cation and anion leave the crystal. So your options are A, both true and reason correct, B, both true but reason false, C, assertion true but reason false, or D, both assertion and reason are false. And the correct answer is D. Both the assertion and the reason are completely false. Remember, Frankel defects do not affect density at all, and the ions definitely don't leave the crystal. They just pop over to an interstitial spot.
Section 6. Toot Guide Practice.
As we wrap up today's explainer, I want to leave you with this direct note from the source. The tool guide section-wise worksheet available for practice. Practice is your absolute best tool right now. Seriously, doing those reps is how you turn theory into test day triumph. You've got the exact past year questions, and you know the core differences between Schottky and Frankel defects inside and out. So the only question left is, will you secure your marks by mastering these specific point defects? Grab that worksheet, get to practicing, and never drop a solid-state chemistry mark again. Thanks for tuning into this explainer, and I'll catch you in the next one.